Suppose a rocket, problem 726. Suppose a rocket is at an elevation of 100 kilometers and has an initial velocity of 1 times 10 to the 4th meters per second directed vertically up. If the rocket engines do not burn and no force other than the Earth's gravity acts on the rocket, how far does it go? Alright, so this is going to be a problem where we apply conservation of mechanical energy, specifically kinetic energy and gravitational potential energy, and we can set the initial kinetic plus the initial GPE equal to the final kinetic and the final GPE. The only force acting on the rocket, which I, in the picture over here, have put in as little m, mass little m, is gravitation. So this picture shows the variables that I'm going to use in the problem. I'm going to have an initial r sub I, which is the distance the rocket is initially from the center of the Earth. That's going to be this distance from here to here. The rocket has an initial v sub I up, and then the rocket keeps on going up until it gets to a final v sub f, at which point has no more kinetic energy. And that final distance from the center of the Earth is r sub f. So if you look at the quantity requested in the problem, how far does it go? And that's this distance here from the initial position to the final position. Essentially, that's the displacement we're calculating. And so that h, the additional distance the rocket goes up, is going to be r sub f minus r sub I. That's this h. It's not drawn quite correctly in the picture here. I meant it to be from there. Okay, so let's go ahead and fill in kinetic energy and gravitational potential energy. So I'm going to have 1/2 mv sub I squared minus g little m sub e, that's the mass of the Earth, divided by r sub I is equal to 1/2 mv sub f squared minus big M little m big G little m times m sub e divided by r sub f. Little m occurs in all the terms. That's the mass of the rocket, and it cancels, so the result's going to be independent of the mass of the rocket. So now let me get r sub f over on one side of the equation. That's what we want to solve for, and that's what I've done in this step right here. I can then divide through by GME, and I can get 1 over r sub f is equal to 1 over r sub I minus v sub I squared over 2 big G times the mass of the Earth. And so clearly then r sub f is equal to this quantity above here to the minus 1. This goes down here. So if we plug the numbers in, we get 1 over 6.5 times 10 to the 6th meters. Okay, let me explain this. Let me write two values in here that we're going to be using. R sub b, the radius of the Earth, I'm going to assume 6.4 times 10 to the 6th meters. And the mass of the Earth, I'm going to assume 6 times 10 to the 24th kgs. And so the r sub I is the distance of the radius of the Earth, that's right here, plus the height that the rocket is initially above the surface of the Earth, and that is given in the problem as 100 kilometers. That's 100 times 10 to the 5th, 100 times 10 to the 5th meters, which is 0.1 times 10 to the 6th meters, and so the total distance from the center to where the rocket is the radius of the Earth, 6.4 times 10 to the 6th plus 0.1 times 10 to the 6th. That's where the 6.5 comes from. Minus the speed, 1 times 10 to the 4 meters per second, the quantity squared, divided by 2 times the gravitational constant, 6.67 times 10 to the minus 11 Newton meters squared kilograms to the minus 2 times the mass of the Earth, which is 6 times 10 to the 24 kilograms. 6 times 6.0 times 10 to the 24 kilograms. And all of that to the minus 1. Okay, so the number here inside before reciprocating it is 2.95 times 10 to the minus 8th inverse meters. And if I reciprocate that, in other words, take it to the minus 1, I get 3.29 times 10 to the 7th meters. And so to find h, that's this equation right here. To find h is going to be 3.29 times 10 to the 7th meters minus the initial r. That's this 6.5 times 10 to the 6th meters. And that turns out to be 2.74 times 10 to the 7th meters. That's the additional distance that the rocket goes up.